But anyway, let me thank the organizers again for giving me the opportunity to present our work here. And I'm also sorry that I can't be there in person with the rest of you in the hall. So this work is a collaboration between my group at the University of Bath and the Argonne National Labs, several groups, in fact, at the Argonne National Labs. The very nice single crystals that we've worked with were grown in Mercuri Kanatzidis' group, who works both at Argonne and also Northwestern University. The teams of Y Kwok and Ulrich Welf provided physical characterization of our samples to support our understanding. Most of the scanning probe microscopy measurements were performed by a very good PhD student, David Collum, who's since moved on to a postdoc in Karlsruhe. And we'll be interpreting our results in terms of a model of 2D magnetic fluctuations, which was developed by our chairman, Alex Koshelev. So this is a brief outline of my talk. I'll start by briefly describing some of the history of the coexistence of superconductivity and magnetism in single materials, and in particular materials where the magnetic ordering temperature Tm is actually less than the superconducting ordering temperature Tc, which is probably rarer than just the coexistence phenomena. I'll give a very brief review of ternary rare earth compounds which were studied in the 70s and 80s, which fall into this limit, and talk about some more general considerations of the coexistence of superconductivity with both ferromagnetism and antiferromagnetism. So the material we're interested in today, here I show you a unit cell. It's a fairly complex material with 4 elements in it: rubidium, europium, iron arsenide. It has a superconducting critical temperature of about 37 Kelvin and a magnetic ordering temperature of 15 Kelvin. So that's well below the superconducting temperature. I'll tell you a little bit about the single crystal growth, some of the superconducting properties of this material and the form of magnetism that it exhibits. And also tell you, to put this into context, I'll tell you about some of the prior investigations of coexistence phenomena in rubidium, europium, iron arsenide. On the face of it, many of our measurements look a little contradictory, so it's good to actually be able to put that in perspective. I'll then introduce you to the technique that we use, scanning Hall microscopy, and then give you an analysis of our experimental results, which involve vortex imaging in these single crystals and trying to probe the local superconducting properties at the single vortex level. So we do that by analyzing the vortex profiles to extract the local penetration depth, and then I'll compare our results with a model of the suppression of superfluid density by two-dimensional fluctuations, and summarize with some conclusions at the end. So the coexistence of ferromagnetism and conventional superconductivity is relatively rare, and in fact materials where the magnetic ordering temperature is below Tc, the superconducting ordering temperature, are even rarer still. But nevertheless, many examples were discovered and investigated in the 70s and 80s. These are, for example, the Chauvel phases, the rare earth rhodium borides, and the rare earth rhodium stanides. Now, of course, as we're all aware, the coexistence of ferromagnetism and conventional spin singlet superconductivity is pretty unusual. Generally, this is blocked because the exchange interaction which aligns the moments in the ferromagnet tends to break the anti-aligned spins in the conventional superconducting pairs. So that's normally blocked. So this generally tends to lead to reentrant phenomena. Here I show an example taken from the system erbium-rhodium boride. This exhibits a superconducting transition. If we look at the resistance events temperature plot here, it shows a superconducting transition just below 9 Kelvin. And then there is an onset of a ferromagnetic state at about 1.4 Kelvin, as indicated by this arrow here. And we have a very narrow coexistence region where the sample remains superconductivity. And then at about 0.9 Kelvin or so, we have a reentrance to a normal state where the superconductivity is destroyed by the exchange interaction due to this ordered ferromagnetic state which is coexisting with it. So ferromagnetism and superconductivity are quite rare. On the other hand, move that away, the coexistence of superconductivity and antiferromagnetism is much more common, and that's easy to understand. If you consider a Cooper pair with a relatively long coherence length, then the pair is actually averaging out over the spin polarization of many of these antiferromagnetically ordered spins, and in doing so they sort of average out the net exchange interaction to something close to zero. So it's much more likely to interact and exist with an antiferromagnetic system than a ferromagnetic system. And here I show an example taken from the neodymium rhodium boride system, which actually shows two antiferromagnetic transitions. Here I'm plotting the upper critical field as a function of temperature, and you can see quite a strong suppression of HC2 as the antiferromagnetism turns on, but it nevertheless survives very easily. And these examples were taken from this very nice recent review paper from Bolovic et al. So more then about the rhodium europium iron arsenide material itself. So the single crystals were grown by heating a mixture of rubidium arsenide, iron arsenide, and europium arsenide in the alumina crucible, which was sealed in a niobium tube under argon, heated slowly to 920 C, held there at 12 hours, and then cooled, and any residual rubidium arsenide was washed out by reagent alcohol. All the details are described in this paper here. So we end up by doing that with these very nice platelet-like crystals, which are nice, have nice flat, shiny surfaces, which is perfect for scanning probe microscopy. If we want to study then the superconducting property of these crystals, we can, for example, look at the resistivity as a function of temperature. That's the red data here. And we see a very sharp resistive transition to a zero resistance state at about 37 Kelvin. And we can also, in parallel, study the susceptibility, the blue curve here, which shows this sharp drop as the system turns diamagnetic below TC. But interestingly, it also shows this second cusp here, which is the signature of an ordered, essentially a 2D BKT type magnetic transition, which we can see now very clearly in the susceptibility, which is nice. And that occurs at around 15 Kelvin. The superconducting properties are shown, well, can be extracted really from this plot here. This shows resistivity data as a function of temperature at different applied fields. Here the fields have been applied along the c-axis, perpendicular to the iron arsenide planes, and here they've been applied in plane. And you can see that while there is some anisotropy here, nevertheless, if you calculate the upper critical fields and also the Ginzburg-Landau kappas, you find that these lie in the extreme type 2 superconducting limit. For example, with the in the c-axis, kappa C is something of the order of 67. HC2 at zero temperature is very large, something like 160 Teslas. And these numbers, in fact, are even larger in the in-plane direction, the AB plane direction. Looking then at these upper critical field measurements, although, of course, the fields are higher in the AB plane than in the along the c-axis, in fact, the anisotropy is relatively low and is only about 1.8 in this crystal itself. So it's not a particularly anisotropic material. Trying then to understand the magnetic properties of this material, we look first at these heat capacity data from Willer et al., which is published in this paper. So the heat capacity shows what you would expect, this normal jump here at Tc, which is the characteristic jump you see for a conventional superconductor. But then interestingly, it shows this second cusp-like feature here, which is the signature again, as we saw in the susceptibility of the BKT or 2D BKT-like magnetic transition. And here we show data for the heat capacity in different in-plane fields along the AB axis, or along the AB plane rather. And you can see the characteristic trend is as you apply the field, this cusp washes out, but it actually shifts to higher temperatures. And that's a smoking gun for the fact that the easy axis is actually in plane. It's along somewhere in the AB plane for the moments, these spin-only moments lying on the European atomic sites. The actual magnetic structure, so we see here each europium has a large spin moment of several Bohr magnetons. The magnetic structure was elucidated by Ida et al. Using neutron diffraction. And what they saw in their diffraction measurements, as they dropped below the magnetic ordering temperature, they saw a new peak here, which was consistent with helical magnetic ordering, helical antiferromagnetic ordering, where the spins are lying within the AB planes, but they are rotating and with a period of 4 unit cells. So in this sketch here, which is just 1 unit cell, you can see that the moments have rotated from being along the x-axis here to being in the plane here. They've rotated 90 degrees or perpendicular into the plane here. What's interesting, though, is to superimpose on this then the zero temperature coherence lengths. So here's the AB coherence length. That's perhaps not so important, but the interesting one is this c-axis coherence length. But you can see is quite small. It's of the order of half a unit cell size. And if you look at this, you immediately appreciate that the superconducting electrons which reside here in the iron arsenide planes must actually have significant interaction with the Europium moments here at the top of the unit cell. So you would expect actually quite a strong interaction, and certainly these are not in the limit where you would expect expect any averaging of the moments or the exchange interaction over one or more unit cells, which are one or more periods of this helical magnetic order, which is actually 4 unit cells high. That's very much larger than the superconducting coherence length that we're dealing with here. So it's an interesting situation. It doesn't really correspond to either example that I started with. It's not a ferromagnetic superconductor, but equally well, it's not a sort of an ensemble averaging antiferromagnetic superconductor either. So let's look at some of the prior investigations of this material. And a number of groups have actually looked at the coexistence of superconductivity and magnetism in it. So here is a nice paper from Stolyarov et al., where they looked at 2 different things. They looked at the infrared conductivity in this material, and they also actually did magnetic force microscopy measurements of vortices in this material. What they learned from the IR conductivity data, they were able to invert these data and calculate the superfluid density as a function of temperature. And you can see they see a small but significant dip in the superfluid density around the magnetic ordering temperature of about 15 Kelvin. The MFM data are also quite interesting. You can see down here, this is the density of vortices as a function of temperature, which has been plotted, which are extracted from these images. And below about 12 Kelvin, actually see a slight increase here in the vortex density, which again is a tribute to magnetic suppression of superconductivity. So these are examples which seem to show not strong, but at least a moderate interaction between the magnetic and superconducting systems. On the other hand, there are other experiments which really don't seem to show much interaction at all. There are some magnetization measurements very recent magnetization measurements by Hamida et al., where, for example, they've measured BC1, the lower critical field, in 2 different orthogonal directions. The most interesting one for me probably is where B is parallel to the C-axis. And you can see that maybe there's a very small dip in BC1 here at the magnetic ordering temperature, but nothing really that's very significant. And you would expect this dip to be directly reflecting any change in the superfluid density. So you might infer from that the superfluid density changes very little at the magnetic ordering temperature. Likewise, in these very recent ARPES data from Kim et al. In this paper, they've measured the gaps on the 3 Fermi surface sheets of the hole pockets at the Z point, which lies vertically above the gamma point at the edge of the Brillouin zone. So there are 3 different sheets here. The inner one is the one with the highest gap, and the outer one is the one with the lowest gap. But again, if you look near the magnetic ordering temperature around 15 Kelvin, it's very difficult to resolve any reduction in the gap, any suppression in the gap at all. So that's quite interesting. So our approach to looking at the problem was to look at the local superconducting properties, and by that we're going to image vortices and try and characterize the local superconducting properties from the vortex profiles themselves. So to do that, we use a technique we've been using for many years in Bath, which is scanning Hall probe imaging. This is a diagram of our 3rd generation scanning Hall probe microscope, which essentially is based on an Oxford Instruments Helix helium-3 fridge put inside a helium-4 cryostat. And really the important part, the sharp end, if you like, of the microscope is sketched here, where we have a sample which is firmly anchored to a 300 millikelvin cold plate up here. The Hall sensor approaches from below. It's manipulated by a triple-axis Atacube micro-positioning stage, which gives us our coarse motion, and then our fine motion and scanning is provided by this piezoelectric tube. It's quite a long one, a 2-inch piezoelectric tube. Our Hall sensor, there's quite a lot, really all of our technology is tied up in the Hall sensor, but it has a submicron cross, which is patterned as near as we can to this integrated scanning tunneling microscopy tip. It really is a poor man's STM tip. It's simply, we create a deep etched maser here, and then we deposit a thin film of gold over the edge of the maser, and then the corner here provides us with a poor but satisfactory STM tip, and we can use that to approach and find the surface and map the surface if you wish. So then we have low voltage and high voltage electronics, which allows us to both scan the surface of the sample and also capture information from the Hall sensor itself, also from the STM tip. And in doing so, move that away, we can, in theory, if we're in scanning tunneling mode, where we're actually tunneling into the surface and using that to attract to the surface, we can simultaneously correlate the surface topography and the surface stray field from the Hall sensor itself. But in the case here that we're dealing with, there is no real topographic structure on our surfaces. They're atomically perfect and atomically flat. So there's very little point in actually mapping the surface topography, and that takes a lot of time anyway. So we typically back off a few hundred nanometers and then scan the surface very rapidly in what we call flying mode and just record the magnetic data. So this shows then our first images of one of our crystals at 30 Kelvin. So before we actually before we mount the sample in our microscope, we actually freshly cleave it. This shows an example of a freshly cleaved crystal where we deposit a thin film of gold on top to make a very good contact with the STM tip on the Hall sensor itself. And you can see we've got this very nice atomically flat plateau here, and we take our data here in somewhere region roughly corresponding to the white cross that I've shown you here. If we take our measurements, then these were all in different field-cooled fields. These are negative fields here initially, then we go through 0 to go to positive fields. You can see in negative fields, we see these black vortices here. As we go positive, they revert to white vortices, as you would expect. Because we're working at quite low temperatures, the scanning areas are quite slow. The piezoelectric coefficient of our scanner shrinks with temperature, and these are about 13 microns by 13 microns inside. And what you can take away from this is that the vortex patterns are actually quite disordered. Certainly we don't see a perfect Abrikosov vortex lattice here, and that's very characteristic of a strong pinning type 2 superconducting material that we're dealing with here. So what we want to do then is generate a rather dilute system of vortices so that no two vortices are interacting. There's very little overlap between the fields of the two vortices. That's what we've done here by cooling in a field of minus 0.8 Ersted, where you can see now these two vortices are quite a long way apart and not really interacting. This is a much smaller field of view of about 6.5 by 6.5 microns. And if you look very carefully at these images, this is at 30 Kelvin, this is at 20 Kelvin, this is at 15 Kelvin, you can just about discern, if you look with lover's eyes like I can, that actually the vortices actually broaden here as you go down to 15 Kelvin. Initially they shrink a little bit and then they broaden. But that's much clearer to see if you actually take a line scan across the middle of a vortex in each case. This is what I've plotted in this panel here. This is the field profile as a function of the spatial coordinate x. And you can see that when we start at 30 Kelvin and gradually cool down, initially the vortices actually narrow a little bit down to about 17.5 Kelvin. But then as we approach the magnetic ordering temperature, we see a pronounced broadening again of the vortex. And then as we go even lower still, it narrows again below that. Now we can do a much more quantitative job of analyzing this data if we fit these data to a model. And the model we choose is a modified version of one that was developed by John Clem many years ago. The formalism is quite standard and straightforward, but there are three main parameters, fit parameters, that enter into this theory, one of which is the lead width of the Hall probe that we're using. In this case, it was about 0.5 micron. Another, which is not so important, is the temperature dependence of the superconducting coherence, that actually doesn't enter very significantly into the modeling. The most important one, in fact, is the scan height, the height at which the active sensor is scanning above the surface of the superconductor. And in this case, we find it to be about 1.45. And it's the error bars, in fact, on this scan height that set the error bars on the data that I'm showing here. So you can see from these fits, the solid symbols of the data and the continuous lines of the fits, that we can fit our data extremely well with one consistent set of parameters as described by this panel here. And that allows us to extract the penetration depth lambda as a function of temperature, which I've plotted in this plot here. And you can see as we reduce the temperature from 30 Kelvin, initially the penetration depth shrinks. As we approach the magnetic ordering temperature and the fluctuations kick in, we see a very pronounced broadening of the penetration depth, almost a factor between 3 and 4. And as we cool down still further into the more ordered helical state, we see then that the penetration depth recovers, if you like, and shrinks again. So how can we understand this behavior? Well, to try and understand it, we have compared it with a model of the suppression of superconductivity due to 2D magnetic fluctuations, which was developed by Alex Koshelev, described in this paper here. The model makes a number of assumptions which are listed here. So we're assuming we have a clean layered superconductor in which a continuous magnetic transition, essentially a 2D BKT type magnetic transition, takes place deep in the superconducting state. And the interaction between the magnetic and superconducting states depends very sensitively on the relative length scales that are involved in the problem, in particular the size of the exchange field correlation length, psi h, psi subscript h, and the superconducting coherence length, psi subscript little s. And really there are two regimes as showed, which are sketched here in this diagram here. This shows the two correlation lengths as a function of temperature. And up in this green regime, which Alex has called the scattering regime, we have the case where the exchange field correlation length is much smaller than the superconducting coherence length. And this is very much like the situation that you have in the case of magnetic impurities, scattering off magnetic impurities in a sort of a doped superconductor. What's perhaps more interesting is this region which is indicated in this sort of orangey brown color, and this is the opposite limit where the exchange field correlation length is greater than or much greater than the superconducting coherence length. And in fact, in rubidium, europium, iron arsenide, this is quite a wide regime in terms of temperature, because the exchange field correlation diverges as the temperature approaches the magnetic ordering temperature Tm, and we're comparing that with the superconducting coherence length, which is anyway very small. The superconducting coherence length at zero temperatures of the order of 1.46 nanometers. So this can be quite a broad region. So those are the assumptions of the theory. There are four essentially input parameters that we have to put into it when we're comparing with it. The first is the superconducting gap at t equals 0, delta naught. We have to put an exchange constant into the theory, h naught. We have to describe the magnitude of the spin correlation length, which is given by this expression, which you can see is diverging at the magnetic ordering temperature Tm. A here is the interatomic spacing of the europium atoms in the AB plane, so that's already defined. So we control the spin correlation length via this parameter here, B. And we introduce the non-locality of the exchange field by this parameter AJ, a so-called non-locality constant, which is typically 2 to 3 times the interatomic spacing of the europium atoms in the AB plane. So in order to compare the model with the theory, we first have to take the penetration depth data, lambda, and convert it to something describing the superfluid density, and we can easily do that. If we construct lambda naught over lambda t squared, this corresponds to rho st normalized by some value of rho s naught. So I plotted that here. This is rho st divided by normalized by rho s naught here, and this is the temperature T. And you can see that then we get now a strong suppression of the superfluid density at the magnetic ordering temperature, which is the inverse, if you like, of the enhancement of the penetration depth at the ordering temperature. The best value of the model fit, which admittedly is only semi-quantitative, is given by this dashed red line here, and the fit parameters here are for a zero temperature energy gap of 2 millielectron volts, an exchange temperature of 15 Kelvin, the spin correlation length given for B equal 1, and a non-locality of 3 interatomic spacings, E3 europium interatomic spacings. So I hope you agree with me that the semi-quantitative agreement is good. There are many questions you might ask about the fit parameters. So the fitted exchange constant of 15 Kelvin, that's about 0.4 of TC, which is relatively small, yet we're seeing, nevertheless, very strongly suppressed superfluid density in this case. The value of the gap of 2 millielectron volts is probably smaller than the one would expect. However, I do emphasize that the model does not capture all of the aspects of this very complicated material, which is a multi-band material. It has different gaps on different bands, and also the assumption that we're dealing with 2D scattering, which is an assumption the model will break down very near Tm, where the spin correlation length diverges. But nevertheless, I think the agreement is certainly very satisfactory. So that brings me then to my conclusion slide. So we have probed the local temperature dependence of the superfluid density in rubidium, europium, iron arsenide single crystals by looking at discrete vortices and measuring the superfluid density by measuring the temperature dependence of essentially the profile of these vortices and fitting that to a model due to John Clem. We clearly see a very pronounced vortex broadening around the magnetic ordering temperature of 15 Kelvin, which we attribute to a pretty strong suppression of superconductivity or the superfluid density near the onset of magnetic order. And the results are really in good semi-quantitative agreement with a model due to Alex Koshylev of the suppression of superconductivity by correlated 2D magnetic fluctuations. There are still, I think, a lot of open questions. It's puzzling that the other investigations of the same material that I showed you suggest that the coupling is weak or sometimes non-existent. But I think that probably reflects how complicated this system is. So we have multiple superconducting bands. Each has a different superconducting gap. Each band contributes a different amount to the superfluid density, and each band will actually interact with a different strength with the europium moment. So probably different experiments are investigating different aspects of this complex problem. So we maybe shouldn't be surprised that they are not always obviously consistent with one another. And nevertheless, I think there could certainly be some interesting applications for these coexistence phenomena. For example, the intrinsic magnetic structure in certainly ferromagnetic superconductors, not necessarily these ones, but there are other truly ferromagnetic superconductors. The domain structure could be maximized to maximize vortex pinning, increase the critical current density, and produce very high field, high current conductors. So thank you very much for attention.